Good morning. Forgot my suit jacket today, so I'm adding my microphone to a lapel there. This week I had the most amazing discussion with Steve Krouse, who is an independent computer programming language researcher, who is basically a bit of a very, very nice genius. And we talked about the difference between a statement and an expression, and how that distinction is what defines a functional language from an imperative language, and what the purpose and goal is of functional languages, what that gives us, and where we are today and where we are moving in the future of programming. And it was so much fun. This discussion is going to blow your mind, and I'm sure you're gonna like it. Before we will move on to the discussion, though, I would like to thank today's sponsor, Linode. Linode provides virtual servers that make it easy and affordable to host any app, site, or project in the cloud. Whether you're a Linux power user or just learning how to code, you can use Linode to deploy game servers, WordPress sites, personal VPNs, and much more. Sign up with the link in the description for a $20 credit on your new Linode account. Do it now. Whoop, whoop. Thank you so much, Linode, for sponsoring today's show. Now on to, the show.
The one actually right after Observable, this Origami Studio, is really interesting, I think, from a functional reactive perspective. It's on the list. You can click on it, Origami Studio.
Oh, yeah.
I think it's like the best. At one point in my life, I had an ambition to create a version of Scratch, which we talked about before, but that's functionally and reactive.
Oh. Yeah.
And so this is like the closest thing I've found that's kind of like Scratch, but also functionally reactive. So you'll see me in like 2 seconds make this really cool, like make something, make a little app that I think I make the circle follow my mouse.
Yeah. Oh, wow.
So done. Like you just saw it. That was the whole app, and now it follows.
That is, hang on, let me see that again.
Yeah, I know. You missed it.
So, so you're taking the mouse position, and then you are unpacking it, and then you are attaching those unpacked values to the oval, and then it starts following your mouse.
Yeah, so this is a phone, not a computer, so there's no, like when I pick up my finger, the mouse goes away.
Yeah.
So that's why it does that behavior, but when your finger's down, it works.
That is really, really interesting. I think that this is the thing with functional programming. I think that this is what we need in order to have functional programming really take off. To have like this visual thing. Because functional programming is, to me, a lot harder to reason about if you are just looking at the code.
Yes. But it lends itself well to visual tooling so much better than imperative programming.
Exactly. Because as soon as you introduce state and like these object-oriented things, that becomes really, really hard, like inspecting things inside of values and stuff. But there's a reason why the most common programming environment in the world, which is Excel, is functional reactive.
Yep. I gave a talk, and this was the point of the talk I gave, that the marriage of visual programming and functional programming will produce something much better than either of them could do alone. And that imperative programming plus visual programming isn't anything interesting. And functional programming by itself is also not at all that interesting. But together, they could, that's what I hope. I don't know if I can predict, but what I hope the future of programming is some combination of functional and visual programming.
Aniket SMK asked, how does clean architecture fit with functional programming? What do you, as in, how would you make a use case that works well with an observable-based structuring of code? Aniket, do you mean like a specific term when you say clean architecture, or just like clean architecture as a general concept?
Yeah.
Um,
What is yeah, the word architecture is a interesting question.
you mean like
What
it's
even is
as in
architecture?
I'm wondering if they refer to like clean, like some clean code concept or something.
Mm, mm.
As in when Aniket says as in when you have several use case objects.
Use case
What is
objects.
what do you mean by use case objects? Like that's a thingy like and each are for a certain action and you're plugging them into a presenter and such. Are you talking about modules?
Maybe what the question is, or what I hope the question is he's asking about composability and reusability, being able to take a thing
Yeah.
from one piece of the code and reuse it somewhere else.
Yeah, that's what I'm getting from the question as well. Is that what you mean, Aniken? Like different how you like have different modules interact and keeping them separate and building them for reuse.
Hmm. I hope that's the question because I love that's one of my favorite topics.
Yeah.
But we could talk about whatever the question actually is.
Yeah, let's talk about functional programming and composability a little bit, because to me like that's actually the extreme reusability of functional programming is, I think it's one of its best cases, like cases for it. It's almost a little bit too reusable sometimes.
Yes, that is true. I think maybe just to take a step back, I'm curious what your working definition of functional programming is.
Mine? Who? Um, the language, like the concept of functional programming is so extremely fuzzy, but to me it feels like I kind of define it as working in a language that predominantly uses very small functions without side effects that you aggressively compose together, compose and reuse. That
Yep.
to me that's the core principle. You try to shove state out until like the very edges of the application and try to keep state extremely controlled.
Yeah.
Ice Cold Witch says referential transparency.
I think in two words, referential transparency is probably gets at most of what of what you just said. Well, I don't know if it gets at it, but I think those two words are it's a very important phrase, referential transparency.
Yeah.
I think I've done a lot of thinking about this, and the article we shared, my DCTP article, the acronym stands for Denotative Continuous Time Programming. And so the word denotative is a word that hasn't caught on. And the reason I use that word is because it hasn't caught on, because any word that catches on, the meaning of it is immediately co-opted by people who don't understand the original meaning. And so functional programming was originally defined by, what was his name? It's in my paper, but it was originally defined, and it had to do with all the things you said, but the meaning of it has become confused. But the word denotative has the same definition, and because nobody uses it, it retains its original definition.
Oh.
And so that's why I prefer to use denotative instead of functional. And what denotative means, there are three concepts. I should be able to list them off really quickly. But basically, you only have expressions and sub-expressions.
Yeah.
So there are no statements. They're just expressions. They're just values.
So can we talk a little bit about the difference between a statement and an expression? Perhaps this is actually a good time to pull up an editor.
Yeah, go for it.
Yeah, let's see. Like I'm unsure. Like the thing is with me is that I'm a very bad programmer nowadays. But a statement would be something that actually affects reality. So I guess that this is a statement, like when we declare the constant, and this is x is an expression because it says that like it expresses something, but it doesn't really assign anything. It doesn't say anything about the underlying reality.
Yes. So I think it's very simple. Statements are side effects, and expressions are not.
Okay. So statements are side effects. Expressions are not. That's a very clean way of defining reality. I didn't know that you could express it that cleanly.
Yes, I have the benefit of reading my history, so I have some clean definitions. So I pulled up the definition I was talking about earlier. Peter Landin proposed the term denotative instead of the term functional in this essay, and the essay is called, I think it's like 1001 programming languages, something like that, or the next 700 programming languages. Yeah. And at the end of this essay is a discussion of like the giants in computer science, discussing the ambiguities in the term functional versus declarative versus denotative versus procedural, non-procedural. So these debates have gone on for decades, and there's a lot of really great thinking about it. So anyways, the definition of Peter Landin, he has 3 parts, and I will copy and paste them into this editor so people can see. Yeah. So there are 3 parts. A, each expression has a nesting sub-expression structure. And so what that means is basically that it's an algebra, like A plus B. Like if you were to parse an expression, so for example, 4 plus 3, this is a tree structure, even though it doesn't necessarily look like it. But the plus is at the top, and the 3 and the 4 are
so it's,
on either end. Yeah, so I guess I can make it into a tree. Well, so if you're familiar with Lisp, you will know that
because in Lisp, to me, exactly, this is what it would be.
And so Lisp makes the tree structure very explicit. You know, so like instead of 3, if you want to place that with plus 2, 1, it looks like this. And so the fact that it's a tree is very explicit.
So with tree structure, you're imagining like a tree with where plus is like the root, and then it goes up into 4 and 3. And that is also, I guess, the principle of the editor where we saw before of Luna. That's why Luna. That's why Luna looks like.
Yes. Yeah. This is why people really like node-based editors, because it visualizes the actual tree structure of your expressions. Yes.
Okay.
Okay. So I'll give you point B here. Actually, I should break it up into 2 lines so people can read it. So each sub-expression denotes, and we'll get back to the word denote because that's a really tough word. It denotes something, usually a number, truth value, or numerical function.
Each sub-expression denotes something.
Mm-hmm.
Usually a number, truth value, or numerical function. Yeah, the sentence makes sense, but I'm not sure if I understand it. Can talk a little bit more.
Yeah, so let me, I'll explain what the word denote means. So denote, you could think of it as the word define. So basically, everything in an expression must, you must be able to represent it as some mathematical object. That's what denote means. So the number 4 in code, the number 4 in JavaScript is not a mathematical 4, but because, you know, numbers in JavaScript aren't numbers in math. They're weird. JavaScript numbers are very weird things. And numbers in computers are very weird things. But roughly, a number 4 denotes the number 4 in mathematics. And so anything in an expression must denote some mathematical object.
Okay.
Yeah, so that one's a really pernicious one to understand, but we could leave it at that for now, and come back to it.
Can we?
Oh yeah.
But so in this case, where the constant accent, like these are these edges of the tree, so to speak. They
Yes.
are sub-expressions.
Correct.
And they must eventually like refer to like a mathematical concept, which is like a number.
Yes.
Or
yes.
or a Boolean or
A function itself. A function is a mathematical idea.
okay. So
A set is a mathematical idea. Math has so many ideas, and it's sad how few of them we use in programming.
all right. But like, what would its sub-expression be if it wouldn't denote? If it didn't denote anything?
Great question. Great question. So there are a lot of things that don't denote anything in programming. So, for example, side effecty things don't denote anything.
Oh, okay. All right. So it can't be like an assignment.
So, yes, assignment does not correspond to any mathematical object. Early computer scientists created new mathematical structures that could denote code. So, like, we invented imperative programming.
Yeah.
And then there were very smart mathematicians who invented mathematical structures that are equivalent to imperative programming, but they're really complicated mathematical structures. It's very hard to work with because imperative programming is a terrible mathematical object.
Yeah, it's
so you can do it. You can make imperative programming denotative, but nobody wants to do that. It's much easier to take mathematical ideas and import them into programming.
Yeah, like Ice Cold Witch says the M word.
Monad, yes.
It's I feel like that is something where as soon as you start learning Haskell, you just go, oh, this is very nice, and then you hit the monad and you go down a rabbit hole of
yes,
like uninclusiveness.
Yeah, and the reason I think is because Haskellers are not honest about the fact that monads, the way they use monads, is they're simply importing imperative programming into functional programming.
Yeah.
If they were just honest about that if you use a monad, it's just a regular imperative programming language embedded within a functional programming language, that nobody would be confused.
Dorek says, if you say monad 3 times, a cold chill blows through the room. It's very important here to say that if the word monad confuses you, that's so okay. Everybody, like, it takes so long, like, into your programming career until you actually understand these bastards.
I agree, but also I want to add the nuance that monads aren't like. Sorry, I mean to say this in the most optimistic way. Like, this is a very positive thing. Monads are not as hard to understand as everyone makes them out to be.
Sure. That's true.
Which I don't mean to say that if you don't understand it, you're doing something wrong. What I mean to say is that. But like, basically,
I do agree.
Yeah.
Like, monads are like, when I learned them, I understood. Okay, people like almost a lot of people. It felt like a lot of people almost intentionally obfuscated this.
Yeah. I think what I'm getting at is, if you have ever done imperative programming, like if you understand the idea that const x equals 3 plus 4, and then const y equals like x plus 1, if you understand these two, if you understand like these two lines of code, you understand monads. All monads is a way to like chain two imperative statements together. So everyone who's listening to this call understands monads. They just don't know that that's the word to use to describe what they understand implicitly.
Yeah, it's very simple. Like, they are not like the code of a monad is rather like the code of what a promise is rather simple. Like, most people with even rudimentary JavaScript knowledge would learn them. It's like the general category model that is just it's so hard to approach.
Yeah, I think ultimately, I think what we're both trying to say is that the people who teach monads do it poorly.
Yes, that is for sure. And I think that is a problem in functional programming in general. The packaging of it is very rarely designed for approachability and niceness.
I think the thing that most functional programmers don't understand is that you need visual programming as well. When you combine functional programming and visual programming, you get Excel, which is used by billions of people. When you take functional programming and you remove visual programming, you get Haskell, which has a reputation for being unbelievably hard to understand. So it's really all you have to do is take advantage of the visual affordances that these mathematical ideas allow.
Exactly.
And then everyone can use it. So, anyways, I'm just going to paste in the third definition of a denotative language. And as I was saying before, I prefer the word denotative instead of the word functional, but they kind of mean the same idea.
So the thing an expression denotes, i.e. its value, depends only on the values of its sub-expressions, not on other properties of them. Okay, so like to me this sounds like this refers to purity or referential transparency.
Yes, referential transparency. You are correct. This is the definition of referential transparency.
Yeah, basically there's no globals in the function, or there is no closures. Like it doesn't reference any variables outside of itself, or like it's just the pure expression.
Yeah, there's no spooky action at a distance, if I were to say it like Einstein would.
Spooky action in the distance. I've never heard that. Like, what did Einstein mean with that? I'm assuming he didn't refer to functional programming.
No, he was talking about entanglement, and basically he was saying that,
which actually is a very interesting word to use for like the opposite of referential transparency.
Correct.
Like,
it sure is.
I almost feel like it's a better word than purity or referential transparency.
Yes. You mean like no entanglement?
Yeah, exactly.
Yes, exactly. Yeah, I have a friend who wrote a paper, and he used the word entanglement to describe the like a language construct he invented. Yeah, but anyways, that's kind of a tangent we probably shouldn't go down. So anyways, just to finish what I started, this is a useful definition of functional programming that I use. I try and be careful, and I use the word denotative instead of functional programming, because if I use the word functional programming in public and I think it means this, I will get into arguments with people, because not everyone thinks that this is the definition of functional programming. So I just use a different word that nobody uses, denotative. And back to the original question that I forget who asked it, but back to the original question of does this provide for good architecture? The answer is a resounding yes. The whole point, the reason we're limiting ourselves in these ways, and the reason we're programming in this way, is for the express reason that the architecture it allows us to program in is so superior than regular everyday programming. And I talk more about that in my essay, but
yeah, but can you give like some teasers?
Yes, definitely. So let's see. The one that I think the one that's most obvious is composability.
Yeah.
And so I spent, I don't know, a couple dozen hours trying to understand category theory, and I know enough to be dangerously incorrect, probably. But
yeah.
But the thing that's exciting about category theory is that it's the study of composability. And so what's really exciting about category theory is it studies what you can do simply with composability. Like the only thing you're allowed to do in category theory is compose things. That's like the only operation that you're allowed to do. And so if you're only, actually there are two things. You're allowed to apply ID, which is identity, which is the function that does nothing, and you're allowed to compose two transformations.
Okay.
And so anyways, functional programming benefits from a lot of the work that category theorists have done on composability. So if you really care about reusability and modularity, functional programming and category theory is the study for you. Like that, this is specifically the thing that those people study. And so there was a really great blog post I read. I may have to put the link in later. I think the people who made something called Statebox, I think that's what it's called. They wrote about how the reason you care about composability is because when you have you want to make a really complicated system.
Yeah.
Every piece of software we make is really complicated. Even simple things have hundreds and hundreds of things that are going on.
What do you mean by complicated
And so,
in this sense specifically? Like lots of things or like intertwined things?
yes. I mean, I'm mostly speaking about the number of things, but the fact that they're intertwined creates a combinatorial explosion, which makes, so it's a perfect storm. We've got both. We have, like, if you wanted to describe to me in words Twitter, it'll be many, many, many books like of words, just in English words or pseudocode. But then, of course, those words are intertwined.
Yeah.
So you're going to talk about something, and then you're going to talk about it over here, and so it's a perfect storm. Programming is the things that software developers create are probably the most incomprehensible or difficult to comprehend things that humans have ever created. I think the environment is probably more difficult to comprehend, but software projects are maybe the most difficult thing to comprehend. So the reason we all hate legacy code is because of this. Computer science is the only discipline where the word legacy has a negative connotation. Usually, like, people want to leave a legacy, but software, nobody wants to adopt someone's legacy.
Oh, I love that. Software development is the only place where legacy has a negative connotation. That's such an amazing quote, and so correct.
Yeah, I definitely can't take credit for that quote, but I forget who I'm quoting. So Google around for whoever gets credit for that.
I'm sure someone in chat will find it.
So a lot of what I talk about is the comprehensibility of code. I think the word readability is too small of a word because code isn't meant to be read line by line. If you're meant to read code line by line, you will be doing it all day because even Microsoft Word is like millions of lines of code, and it would take you a lifetime to read millions of lines of code. So readability, let's throw that word out. Comprehensibility. If, let's say I'm a developer at Microsoft and I'm working on Microsoft Word and there are millions of lines of code, but all I want to do is change the color of one button, or I want to make two buttons interact in a way that they don't now. What's the minimum amount of code that I need to read in order to comprehend enough to actually make the change that I want to make? And so that's comprehensibility, and that's the most important thing. Programmers spend half or more of their time reading code. This is an established scientific fact. And so a language that lends itself well to comprehensibility is amazing. And denotative languages really lend themselves to comprehensibility because of this tree structure and because of the lack of entanglements. So the tree structure, if you put me anywhere in this tree structure, so let me just back up for a sec. So imagine if Microsoft Word was described as in a denotative language. If Microsoft Word was built in a denotative language, the entire program would be one expression. So there's no statements. Microsoft Word itself would be one expression, one big tree. And so the question is, I want to navigate this tree to figure out how it works enough to make a change to this tree. And so what's great about the fact that it's a tree and the fact that there are no entanglements and each sub-expression is fully defined by its children is that I can rifle through it like it's an encyclopedia. So the metaphor I use here is that it's the difference between prose, regular writing, like Harry Potter, and an encyclopedia. So if you want to know what happens to Hermione Granger, you have to read 7 books about this Harry Potter guy. You can't just skip to Hermione Granger. You have to read about every other character. But if you want to, but with an encyclopedia or Wikipedia, you can just Google Hermione Granger and read everything you want to read about her. And so this property is what makes denotative languages so much easier to understand them. And it's a really valuable property.
Yeah, and we do see benefits of adopting this in front end and in real life. It feels like the one-way data binding or one-way data flow that React introduced into the front end industry was so profound in how much they managed to simplify applications. When you knew that data just flowed one way and it was effectively like this tree of functions, and it always updated up until the tree. And it's been so powerful that pretty much all the frameworks that have been created since have adopted that one-way, one unidirectional data flow, which talks a lot about like, which I think about when you describe this and the simplicity
Yes.
that it does gives us.
Yes. Yeah, and I think it now is a perfect time for me to mention that React didn't invent this. What my DCPT article is about the actual roots of functional reactive programming, which is like something that I think our culture doesn't like pay enough respect to.
All right, so hang on, like let's how do I find this article?
Here, I'll paste the link in for you. I'm on it right now. I will just say that most people don't really like this article. So
good, I like those articles.
So it's futureofcoding.org/essays/DCTP.
Oh yeah. Okay. No,
it's in the
no,
chat
oh, no,
somewhere
no,
already.
No, no, which article it is. I just make the connection of DCTP.
Yes, exactly.
I'll also update the Twitch box with this.
So I originally found React and Redux, and I fell in love. And it wasn't until much later that I worked my way back to Connell Elliott, who created FRP in the 90s. So this stuff has been around for a very long time.
Yeah. So FRP was invented in the 90s. That is so cool. But it's like it's also cool that I thought that more or less it feels sometimes when I read about the history of computer science, it felt like all of it was invented in the 70s. So I'm glad that somebody invented something in the 90s.
Yes, that is true. That is true. And people are still inventing things today, but it's almost like 1% of the things that seem to be invented today are actually invented today, and most are just rehashing things done in the 70s and 90s and 80s too.
Yeah, but it's I think that's pretty cool though. I like that ideas are not forgotten. That gives me comfort. Because like for instance, like machine learning is one of those things that that was developed way back, but we just didn't quite have the computer it just didn't make sense at the time because you didn't have the vast machine parks and graphics cards that we use to make it feasible for most applications.
You know, I just was speaking to someone who works at OpenAI, and he was telling me about how we're about to reach the neurological equivalents in silicon. Sorry, I just made that phrase up. What I mean
I get like
is
a computer that is as powerful as a brain.
It has as many connection possibilities as the human brain. Basically, yeah, has the processing power of the human brain. We're almost there, and then it's really just a matter of time until we develop strong AI because we already have the proof. Like, if you believe that there's nothing magical about this processing power, if I have a piece of silicon that has the same processing power, we just got to figure out the software.
Yep. Oh, that is interesting for sure. I don't want to use the term scary because that implies like a pessimism, but it's a little bit scary.
Yeah, sure. It sure is.
Yeah.
It sure is.
Yeah, but then again, we do have nukes, and like we're not using them too much.
Yeah, technology is scary because it's an extension of us and our wills, and so like the question is, what do we do with it? You know, like a hammer is a scary. A baseball bat, you know, these are scary pieces of technology because if someone wants to kill you and they have one, they can kill you. But they're also amazing technologies in the positive things you can do with them.
Shandy has a really interesting question here. I wanted to know, why did we need statements in the first place in programming if expressions are enough?
Great question.
Is, right?
That's a really wonderful question.
Because I kind of like what comes to mind here, then you can probably give a better answer, but I just want to use it because I just love the statement. The creator of Haskell, it says in an interview, like, well, a program that doesn't have any side effects is not particularly useful. The only thing that it does is makes the computer warm.
Well, so following on that, clearly, the computer being warm is a side effect.
Yeah.
And so I bring that up because I want to make it clear that even though Haskell programs pretend like they have no side effects, they do. They make your computer make noise. They make your computer warm. They maybe make you smile or make you frown. It is impossible not to have. The only thing that doesn't have side effects are inert things. And even inert things have side effects. So anyways, this gets philosophical, but it's one of my favorite topics. But I find it really hard for people to grok. So if you don't get it, I'm just going to kind of like throw a bunch of different metaphors, and maybe one of them will stick. Let's see. So when we the history, let me kind of paint a picture of the grand quest of functional programming. Most functional programmers don't even realize there is a grand quest. And many of the functional programmers who embarked on a grand quest have since lost the vision. But here's the vision. The vision is, how can we eat all of programming? How can we take all the statements that other programmers need in order to make their computers do the things they want their computers to do, and eat them in such a way that the interface we expose to the users of functional programming languages are pure expression, referential transparency, all that good stuff. And so one example that we have eaten, we have conquered, is mutability. The reason we needed to mutate variables is because we didn't have enough space. If you had a big data structure and you wanted the same data structure with one thing changed, you couldn't create a copy of it with just one thing changed, because there's not enough space for that. So what we've done is we've come up with these really fancy algorithms so that under the hood we just have one thing and there's just a delta. So functional programming languages under the hood use mutation as their implementation strategy, but the interface it provides to the programmer is that things aren't being mutated.
What do you mean that they uses mutations under the hood? Like, do you mean like they fiddle around with memory, or? Yes,
exactly. So the thing is, we need statements, but the proper place for statements is in the implementation layer of the programming language itself.
Yeah. So
the implementation of Haskell.
Ice Cold Wish, which says, and basically maybe he's quoting you, is or her basically trying to express every side effect purely.
We want to enable any side effect that someone might want to express. You should be able to express it in a pure way.
Okay. And that would be like, what does that mean in practice? Is that sort of like the actions?
I have a
Redux?
great example. Oh no. So the actions in Redux are examples of things we haven't yet eaten. Like, those are things that the functional programming community needs to eat.
Okay, so
it's a thing we need to conquer.
Okay, so you have like your functional space over here where all the things are nice and pure, but then you have actions over here. Like we have walled them off in a nice little space.
Yes, and so if you think that actions are okay, you have lost the vision. The vision of functional programming is to make the need for actions. We'll always need some actions, but to continue to eat them. So let me give you the perfect example: functional reactive programming. Before functional reactive programming, and you wanted to make a website, you had to use jQuery by hand to side effect the DOM piece by piece. Yeah. When I used to use Haskell to do web programming back in the day, back in college, I was using a monad to affect the DOM.
I'm really liking this. Let's have a look at jQuery to remember what where we've gone in programming. Actually, this is really interesting.
Yeah.
So if we look here, this is I think that this event handling code here is a great example. We grab this reference here for like a banner message and put that into a variable. So actually, like, banner message here can actually be destroyed like in between the execution of these two lines, hypothetically.
Correct.
Well, or not quite, because JavaScript is synchronous, blah, blah, blah. But then it gets this button, and then it attaches a click handler to this object. And then that click handler is actually attached here, so that's actually more state. And then once we have an event, we go and manipulate the state of the hidden box. And this is super simple code and super understandable in this context here. But as soon as something goes wrong, and it is so hard to figure out what the hell is going on.
Yes. It's so I think if you looked at this code, or you showed me this code back before React and functional reactive programming took over, and you said to me, like, this is proof that functional programming stinks, I would agree with you, because I've tried to do that kind of coding in Haskell and it's impossible.
Yeah, precisely. If you try to do it with that approach. However, what React taught us is to do things like this on the React documentation, where we just the code you just have this declarative language, which is HTML, and then you use declarative properties in it. Like this div here that always contains this prop's name. We don't actually go in and get a reference to this div and manipulate things. But this only makes sense because React provided this declarative structure that we can work within and show the way.
Exactly.
Sorry, I was interrupting you.
No. You made my point. That's exactly it. The thing that, to drive the point home, the thing that you have to realize is that you can't look at a statement and think, how do I functionalize this statement? Because the way to functionalize a statement from an imperative language is to just put it into a monad, which is a cheat.
Yeah.
Monads are a way to cheat until we come up with the actual right way to totally change our way of thinking, such that you don't even have to copy over the imperative lines one by one.
So would you say the virtual DOM, is that a sort of cheating, or is that a correct abstraction?
Correct abstraction, because the virtual DOM, it takes imperativity and puts it into the implementation layer.
Yeah. Oh yeah. So we want the stuff out of the implementation layer. We could probably find a better way, a more effective way than the virtual DOM. Say perhaps I know that Svelte is trying to have a pre-compilation step, but or a compilation step, but it's still essentially the same principle that you're talking about here, right? That we both are shoving the side effects out of the code that the programmer writes and out into into the programming framework.
Yes, exactly. That's the quest of functional programmers. That's the crusade that, in my opinion, true functional programmers are on, to continually put things into the implementation layer of the functional programming language or framework.
I see. That is super cool. I love it.
And one thing to point out is that it's a never-ending quest, because computers, the edge of computation, they'll continue to invent things that don't neatly fit within our existing functional programming abstractions. And so it's a continuous, never-ending game. I actually think about it as we're chasing a moving target.
Yeah.
And so edge computing is moving like this, and functional programming is moving like this, and we're always going to be some amount behind.
I hope you enjoyed that discussion with Steve Krouse. I certainly did. Don't forget to check out our sponsor Linode, link in the episode description, VPSs, and wonderful stuff. Do it now. If you're new, this show is called Fun Function. I produce new videos and streams every week. You can check us out on Twitch at twitch.tv/funfunfunction, or you can subscribe to videos right here if you want videos. And if you're a bit uncertain, you can also check out this playlist right here to see what the show is about. I am MPJ, and until next Monday morning, stay curious.